Okay, so we can calculate energy, and that's pretty boring unless what we're really interested in is changes of energy. So increases of energy, decreases of energy, changing the energy of systems. And so what we're interested in is a principle that lets us understand how energy changes due to inputs from the surroundings. And see, these principles always seem to have something to do with change. And so we're looking for a principle that tells us how to calculate inputs from the surroundings. Now, where we're going to end up eventually is a principle that looks like, very much like the momentum principle did. So, for some system, we're going to choose a system. We're interested in comparing the initial energy, we're calculating the final energy of a system after something happens from the initial energy. And it turns out that the kinds of inputs the surroundings can make include an input that's called mechanical work. And this is one of these, so it's called work, one of these physics words that doesn't mean the same thing it means in ordinary language, so then we have to be a little careful. And what's work? Well, remember that when we were changing momentum, when we had the momentum principle, we had the future momentum of a system was equal to the momentum now plus the net force, the impulse which involved the net force and a time. What we never actually looked at, though, we never asked what happens if you take a force acting through a distance, through a displacement instead of a time. So what work does is it involves forces and displacements, distances. And it's actually sort of moderately intuitive. This is a pretty heavy book, so one has to expend energy to lift it. So if I lift it half a meter, I've burned some of my Cheerios for breakfast. If I lift it twice as far, presumably I've done twice as much, I've expended twice as much energy. So if I exert the same force through twice the distance, I've presumably done twice as much work. And that's what work turns out to be. It has to do with force acting through a distance. So we can actually write this provisionally as, here we had a y component of a force acting through some displacement delta y. And so instead of a delta t, force time, we have force displacement. But things don't only just move in one direction. We live in a 3D world. We can have displacements in a 3D world. So let's consider a situation like this where we have, suppose that you and your friend are pushing a box across the ice in a hockey rink. And so you're looking down, so our axes are x and z. We're standing on the y-axis looking down. Okay. And you exert some force F in the x direction, and the box moves some distance delta x in the x direction. But your friend is pushing in the z direction. So your friend exerts some force in the z direction, and the box moves some amount, probably a larger amount, in the z direction. So the box actually moves during the time you guys are pushing. So the total displacement of the box would be some delta r that way. Well, you do some amount of work, fx delta x. Presumably your friend did some amount of work, fz delta z. So what do we want to do with those two things? Just add them together, don't we? So in fact, it's going to be force in the x direction times displacement in the x direction plus force in the y direction times displacement in the y direction. And that's going to be what we define as work. So and if there really is very little friction, and you push in the x direction and your friend pushes in the z direction, what's going to happen? The box is going to not only move, but speed up, right? So its kinetic energy should increase. You put in energy, you're in the surroundings, you put energy due to work, the kinetic energy of the box increases. So we have work done by forces, Fx delta x plus Fy delta y plus Fz, change in z. So there's a notation that comes from vector algebra that we use to summarize, and this is true as long as the force is constant over those distances. And if it's not, we have to worry about taking smaller steps and adjusting for that. Just like we did with using the momentum principle. If a force was constant, we could take big time steps, but if it wasn't, we had to take little time steps and recalculate the force. We have to take little distance steps here and recalculate the force. So so this is a definition. This is work. And notice that x components of forces can be negative, or delta x's could be negative, or any of these things could be negative. So work, it looks like, could be positive or negative. And that makes sense because it's going to change the energy of a system. It might make it go faster, it might make it go slower, so that's okay. There's a compact notation written this way. It's the vector f, because we have all the components here, dot vector displacement, where the vector f is, of course, fx, fy, fz, and this delta r is delta x, delta y, delta z. So this is called a vector dot product. It's one of the legal ways of combining vectors, and it's just a compact way of writing this. This is what it comes out to. The result is a scalar, not a vector. What you do is you take fx multiplied by delta x and add that. So that's what that is. Okay? So if we write this, you need to think I'm adding up these quantities and I'm getting a scalar. So we haven't done anything new. We've just introduced a new notation. Okay, so let's think about how negative work could be possible. So we have E final for a system is E initial for the system plus work. And there could be some other inputs, but for right now we're not going to. This is work. We might even write work done by the surroundings, just to remind us that it's done by the surroundings. Or we could write the change in energy of a system is work done by the surroundings. So let's think about how this could come out to be negative. So let's just consider some examples and think through them, what the possibilities are. So we started with, we'll do it in one dimension just to be simple, but it extends to all three. So we've already started out with a box. There's some force in the x direction. There's some displacement delta x. So let's get some numbers. Okay, so let's say this force is plus 3 newtons in the x direction. And delta x, which of course is x final minus x initial, that's plus 2 meters. And so the work done here is going to be 3 newtons times 2 meters, 6 joules, so joules a newton meter, that's positive, so that didn't come out negative. So let's look at some other situations. And one way to consider these other situations is to think, if you're confused, think about numerical examples. So we've just been watching a lot of figure skating on television. So we have a figure skater sliding in the plus x direction along the ice toward her partner. When she gets close, he pushes on her in the plus x direction, slowing her down. So what's the sign of the work he does on her? So she's traveling that way. He's exerting a force that way. Okay, well, most people say it's negative, but a few people say it's positive, so let's use some numbers. We'll just use, I know figure skaters, well, it would actually maybe work. So let's say the force in the x direction was 3 newtons. Delta x is this way. That means that somebody started here and went there. So let's say at some coordinate system, this is 5 meters, and that's 3 meters. So delta x that's the final, isn't it? So we have 3 minus 5 meters. So delta x here is a negative 2 meters, right? So we have negative 2 meters, and therefore the work done was 3 newtons times negative 2 meters, not. And so that looks like negative 6 joules. So he did negative work. Now, does that make sense for the energy principle? She starts out with some amount of energy. The surroundings do negative work, which means her final energy is less than her initial energy. She got slowed down. Okay? Questions about that? Okay, let's try another one. It helps to put in numbers. So here's a fan cart moving in the minus x direction. We have a force by the air also in the minus x direction. Is the work done by the air positive, negative, or 0? Okay. Most people say that it is positive, so let's try some numbers. This would be negative 3 newtons. And where's the purple marker? There it is. This would be a negative 2 meters. So we have work is negative 3 newtons times negative 2 meters, and it is indeed plus 6 joules. So positive is right. Last one. Your skater on a skateboard is coasting in the plus x direction. His friend doesn't want him to run over her, so she pushes in the minus x direction. Okay? Most people say positive. Wait, negative, sorry. It was 2. So we have negative 3 newtons. We have plus 2 meters. So we have negative 3 newtons plus 2 meters, negative 6 joules. So let's see if we can summarize this. There must be a pattern here. So here are the situations we had. We had the force, the displacement, and the work. So there were first two had the force to the right, and the next two questions had the force to the left. We had a displacement to the right and a displacement to the left and a displacement to the right and a displacement to the left. And we came out with positive here, negative here. This was, oh, that's that. That's negative and that's positive. So what determines the sign? Is it the direction of the force? No. Is it the direction of the displacement? So what is it? Yeah, it's the relative direction, isn't it? So if they're in the same direction, looks like it comes out positive. And if they're in opposite directions, it comes out negative. So it's the relative directions of the force and the displacement that determines whether the work is positive or negative. In each case, it made sense, right? You're slowing something down or speeding it up. Right? Okay. So that gives us sort of a physical way of thinking about what the sign of work ought to be and of understanding why it makes sense that it can be positive or negative. So what we want to do is we want to get to a point where we can actually apply the energy principle to calculate something. But there's one case we haven't considered. So let's take care of this one. You've got a box on ice. You're pushing the box so that the box is moving that way. But your annoying little brother is actually pushing down on the box. Yeah, he's pushing down. So how much work does he do? That's right, he does zero work, doesn't he? Because what we have here is this would be 0 minus F0 if we write it that way. And this would be delta x 0, 0. And so if we work it out, the work is 0 times delta x, whatever that was, plus minus F times 0 displacement in the y direction, plus 0 times 0. So it looks like if the force is perpendicular to the displacement, if we get this right angle here, the work done by it is 0. So same direction, positive work, opposite direction, negative work, perpendicular, no work. Now there's one other situation that may come up, and we've already done some things like this. Remember the problem where you're pulling a sled across the snow and there's some angle here. So you pull up at an angle, the sled moves that way. How much work did you do? Well, what we want to do is we want to think of this force as having two parts, which of course it does. It's got Fx, Fy, Fz is 0 here, so we might as well write 0. And delta R is delta x 0, 0. So the work done looks like it's going to be the x component of the force times delta x. And the y component of the force isn't actually going to do any work because there's no displacement. And so now we just get back to the use direction cosines to find the force expressed. So if you're given the magnitude of the force, we know that that's equal to, what do we have? We have cosine of, let's say this angle here is 25 degrees. So that would be cosine of 25 degrees. That's the angle to the x-axis. This angle here is cosine of 90 minus 25. The z-axis, of course, is cosine of 90 degrees. Okay, so you can do that. And so there's another way to, so there are various ways to evaluate this that you may need to work on evaluating this thing, which is written in shorthand as a dot product. Okay, so let's actually work a problem using the energy principle just to see how this might play out. So we have suppose that you've got an air-propelled cannon and you shoot a baseball straight up. A baseball whose mass is 0.15 kilograms, moving straight up at 20 meters per second. At a later time, it's moving up at a speed of 15 meters per second. How much work was done on the ball by the surroundings, first of all? And then, second, how far did the ball move? Now, when you see a problem like this, it's reasonable to ask yourself, can I just calculate these quantities directly? I know how to calculate work. Can I calculate the work done by the surroundings on the baseball directly? The answer in this case is no. I can't just use the definition of work. Why not? Does work say anything about constant speed? No. So we have work is fx delta x plus fy delta y plus fz delta z. So what don't we know? Yeah, we don't know how far it moved, do we? We probably know the force that it exerted on it because what's in the surroundings? The Earth, right? So it's probably the gravitational force near the surface of the Earth. So that's not a problem. We can neglect air resistance. But we don't know how far it moved, do we? So we can't calculate work directly. But can we use the energy principle to calculate work? So here's the energy principle. We have E final is E initial plus work done by the surroundings. Yeah. This is what we want to know. Here's the unknown. So if we found E final and E initial, we could get it, right? Can we find them? Yeah. So how do we do that? Well, the way we do it is we write down all the terms that appear, first of all. So considering the baseball as a particle, we need to write down its energy, and we're going to write it in the form of kinetic energy plus mc squared. Okay, that's its total energy. And plus the work done by the surroundings, and that's the initial value. So K initial plus mc squared. And now we have the final. This is final kinetic energy plus mc squared. And now we look at this and we say, okay, what things do we have to calculate? Did the rest energy of the ball change? Now, we'll talk more about this next time, but a change in rest energy is accompanied by transmutation. Uranium turning into palladium nuclei or something like that. So it's the same ball. So that's the same. So no change. So now we get K final minus K initial is equal to the work. And how are we going to calculate the kinetic energy? A half mv squared. So we have a half times, what do we say, 0.15 kilograms times the final speed is 15 meters per second squared minus a half times 0.15 kilograms times 20 meters per second squared is the work done by the surroundings. And so what do we get? So you could simplify that algebraically if you wanted to. I think that comes out to 30 joules. And I think this comes out to about 16.9 joules. Is that what you got? And so it looks like that's going to come out to a negative 13.1 joules, something like that. Does that make sense? Let's draw a diagram. Let's draw a diagram. So here's the ball. It's moving up, so there's a delta y. You said the force was due to the Earth. So since the displacement is opposite to the force, Looks like the Earth did negative work on the ball, decreased its kinetic energy. Okay, how far did the ball move? What's delta Y? How do we figure that out? Now we can use the definition of work, right? Because now we know how much work was done. So we can say work by the surroundings was equal to Fy delta Y. This was a negative 13.1 joules. This is, of course, equal to a minus mg. So we have minus 0.15 kilograms times 9.8 newtons per kilogram times delta Y. And so we come out with some number for delta Y. Point what? So 8.9 meters, and it's positive, and that looks right. So that's a simple example, but it makes several points. One is you can calculate the amount of work done by looking at a change of energy by using the energy principle. You don't need to be able to calculate it directly, and once you've done that, you can find various unknown things. Okay, next time we get to talk about change of rest energy, change of identity, interesting things like fission and fusion and neutron decay and alpha emission and good stuff like that.